Okay, guys, I'm going to start now. So, welcome to Training Smart Agents with RL. So, I'm going to go through what is RL first of all, and then pure learning basics, which is like the fundamentals of RL, and then Critic Networks all the way to PPO and ACs. And then at the end, we're going to do a workshop. Okay, so what is RL first of all? So, what? Oh, okay. Okay, basically this is RL. So we have an agent and an environment. So the agent will be interacting with the environment. So the agent will first take an action in the environment, and then the environment will return agent's rewards and the state that the current agent is in. After that, the agent will use that basically state and reward that the environment has returned to make a new action as well as to train itself to make better actions. And then it just repeats. So that's like the fundamental idea of RL. There's some technologies we have to go through. So first of all, let's go through observation space. So basically, an observation space is the information that the agent gets from the environment. So there's two distinctions. The first one is a state. So a state is when an agent can see the entire environment. And then an observation is when the agent can see only partial details of the environment instead of the entire environment. So I mean, you can see in this chest environment, like you can see everything. But then in the right side, in the right image, you can only see like what part you are in, like of the map, but you can't see the entire map itself. But we use both terms like as the same essentially, so it should be fine. There's also the action space, which what an action space is basically what actions the agent can take. So there's again two distinctions. First is discrete actions, another is continuous actions. So discrete actions, obviously you can count them now. So it's like forward, back, attack, jump. Obviously you can count those actions. Continuous actions is where, for example, in this environment, the action that the agent can take is any number from -1 to 1. So like negative 0.9, 0.9, 0.8, 0.7 is included. You can't count them. It's like infinite number of actions. So we call them continuous actions. And then we also have the reward. Basically, every action that the agent takes in the environment will basically give a feedback to the agent in basically a reward. So every action that the agent takes, there will be a reward tied to it, telling them like how good their action is in this state or how bad their action is in this state. So there's a cumulative reward, which means like in one episode, the total number of reward that the agent has been given. And then there's a discounted cumulative reward, where we just put a variable gamma for every reward after t plus 1 times that t plus 1. This is to basically discount all future rewards, because there are times where, for example, 5 steps later, you don't know, like, you're not going to be super sure like how good that state or taking an action in that state is, especially for future states. So you're going to be more sure of the actions and the state that you're in, which is like closer to you now. And then it also helps with capping the reward, the cumulative reward, to prevent divergence to infinity. Because if you don't have this discounting factor, your cumulative reward can go up to like however many that like the environment gives. Like there's no cap basically. So the goal of the agent is to maximize the cumulative reward, obviously. And then yeah, this is an example. So for example, we have this maze here where every grid has a number assigned to it. So you can think of every grid as a separate state that the agent can be in. And then the actions are obviously going up, down, left, and right. And then for the discounted cumulative reward, let's just assume we have a discount factor of 0.9. So gamma is 0.9. Sorry, these gammas are supposed to be gamma RT plus 2 plus gamma squared RT plus 3 plus gamma cube RT plus 1. So let's just assume gamma is 0.9. So for example, grid 13 would have a discounted reward of of 0.9 to the power of 1 times 1, which is 0.9 essentially. So that's what the discounting would look like. And then there is MDPs as well, Markov decision process. So what an MDP is that it's a model for sequential decision. So it states that the agent only needs the current state and the current action to decide the next action that it will take. One property of MDPs is that you don't need the history to make a new action. So you don't care about the history, like whatever actions you took at first. You only care about the actions you just took. And then you make a new action based on that. And then it's formally defined by a 5-element tuple, which is S, A, P, R, and gamma. So gamma we already explained, which is discount factor. Then S is the set of all possible states. A is the set of all possible actions. P is okay, P is transition probability to S from the current state S after taking action A. So it's basically the probability of going to a certain state where you have taken an action A in a current state already. So you can think of it as a probability of going to somewhere from where you are. And then R is the reward function also. And then, okay, let's just give an example using the environment that we have. So like, for example, using this maze, right, the set of all possible states that you can be in, the agent can be in, is essentially the grids 0 to 15. So it can be anywhere from 0 to 15 line. And then the actions that you can take, obviously, you already know up, down, left, right. And then transition probability is like if the current agent is at grid 8, and then it wants to basically go down to grid cell 12. It will be like a probability of 0.7. And then if it wants to go up into the grid cell 4, it will be like a probability of 0.3. So that's what transition probabilities mean. And then the reward function, we can, for example, model the reward function as we give the agent a plus 0.1 reward if the agent is closer to the end, essentially the goal chest, and a negative 0.1 reward if the agent is further away from the end. And then the discount factor would be like, I mean, we showed that already, 0.9. Okay, so essentially this is how the reward can look like now. So the agent starts from the starting of the maze, and then if we are like giving it 0.1, every time it takes a step closer to the goal chest, it will just look like this. And then if it goes further away, it's negative 0.1. So it's quite simple. Yeah. And then we have also something called exploration versus exploitation. So exploration is where the agent takes random actions. For example, if we have this maze over here, if we set the agent to be purely explore on like exploration mode, right? It will just like explore like the starting point. Like it will never go further than anywhere further away from the starting point. So it will just be stuck at the starting point, like taking random actions. And then for exploitation, it means that the agent will only take actions that it sees as high rewards. So if it doesn't see the gold coins and it has only saw like the gold chest, it has only ever gone to the gold chest before, it will just keep going to the gold chest over and over again. Like it will never take any other actions or like explore the path to the gold coins. So the key is to balance both of them essentially to get the best of both worlds. The best of both worlds. So too much exploration, obviously you're getting stuck at the start with little to no progress. And then if you have too much exploitation also, the agent will obviously miss out on the better paths. For example, just now, it missed out on the gold coins, right? So maybe like going to the gold coins, initially you will lose out on reward because you're going further from the end. But in total, the cumulative reward will be more than going straight to the gold chest. So we want to balance both. So one very commonly used method is epsilon greedy with decaying epsilon strategy. What this means is that we have this variable called epsilon. We set it like a high number normally at the start of training, like 1.0 or 0.9. So this means that the agent will, for example, if we set epsilon to be 0.9, the agent will 90% of the time take a random action, and then 10% of the time it will take the best action. And then slowly but steadily, we will decrease epsilon, the value of epsilon, while training. So the agent will initially explore a lot, and then as it goes on training, it will stop exploring, and then it will just like go further into the maze essentially, while also exploring to find possible good paths that you can take. So I mean the code, if you're like if you understand code better, the code is on the right side, but it's quite a simple. Okay, so to show how epsilon can affect the agent, if you are on episode 1 or episode 2, for example, one episode is like you put the agent in the environment and then you let the agent roam around. That's one episode. If you have like an epsilon value of 0.9, no matter what episode you're on, it will just explore like in the start. Like for example, on the left side, it will just explore around in the start, and then the right side it will also do the same thing, but it will never reach the gold coin or the gold chest. And then slowly but steadily, we will essentially decrease epsilon. So this means now with an epsilon value of 0.7 at episode 100, the agent will only take random actions 70% of the time. And then it will take the best actions 30% of the time. So this means that it will basically go to the path where it gets the most reward, but at the same time, it will also explore as much as it can. So yeah, the more you reduce epsilon, the further away from the start it will get to. And then now is Q&A.
Okay, hi. I'm Jovan, and I'm really bad cough, so like forgive me if I cough too much. Okay, so anyway, I'm going through Q learning and deep Q learning. Before we move on to how the training works, I want to talk about the Q table and the Q network. Okay, so this is a more step-by-step explanation. Okay, so a Q table is basically what is used in Q learning. Okay, and a Q network is used in deep Q learning. So a Q table is basically a 2D array. The rows represent the states. States are the grid the agent is on. So if the agent right now is in grid 8, it's very small, but it's in grid 8, then the state will be 8. Yeah. As for the Q network, it's basically a neural network. And if the agent is in, okay, wait. Yeah, if the agent is in state 8, it will basically be one hot encoded. So it will be 7 zeros followed by 1, and then the remaining will be zeros. I will talk about that later. So this is an example of the Q table when it's fully initialized. So these are not like actual values, these are just like made up. So for example, in each row, there will be a highest value which I highlighted. So you can see in the first state, state 0, 0.2 is the highest. And you can see that the action, the columns represent the actions. So left up, right down. So you can see that the best action is 3, which is going down. So if the agent is right here, it will go down, because if it moves towards the right, it will die out. Yeah, so following this Q table, the agent will just eventually go towards the treasure chest and complete the challenge. Okay, moving on to Q networks. So this Q network represents the agent in state 0, not in state 8. So let's say the agent is in state 0. The first value will be 1, followed by 15 zeros. So this is basically one hot encoding the state. So this is just a simple representation. In an actual like environment, which is like more complicated, it won't just be like 1s and zeros. And we will go through that in the coding later. Yeah. So and then eventually you will go through the network, and then you will get the values, the Q values in the output layer. So basically, each node represents a specific action, and you can see that the highest Q value is 0.31. It's going down. So the agent will go down if it is in state 0. Okay. Let's talk about the Q learning formula. So what this formula basically represents is basically means start with what you know. The starting Q value in state S, taking action A, and then add a small adjustment to it. So let's break down this solution, this equation into a smaller bits. So as you can see in this part, this equation, it basically is the temporal difference error propagation. So it answers how wrong was my last estimate. Okay. And the other values represents this is the OQ value before the update. A is alpha, the learning rate. Learning rate is normally between 0 and 1. So a high learning rate basically represents that the agent is learning from the most recent, is always learning from the most recent experience. Whereas if it's 0, the agent is like not learning at all, so like it won't solve anything. Then R will just be the reward. Gamma will be discount factor. So discount factor is also set to between 0 and 1. High gamma, a high discount factor represents that the agent will just strive for long-term rewards instead of immediate rewards. So normally we want a high reward, so we set it to a high value, normally like 0.99 or around there. And then the max Q value of the new state. I will talk about this in the next slide. Next slide, yeah. Okay, before that, another terminology. So how there are two ways to initialize the Q tables at the start. Okay, the first one is we set it all to 0. This is called zero initialization. Okay, so initially all the tables, all the values in the Q table will be zeros. And how will this affect the agent? So this is a neutral approach to Q learning. It basically makes the agent just explore it, and it makes it highly dependent on the exploration strategy. So for example, the epsilon greedy. Whereas if you initialize the table with ones, if you encourage the agent to believe that every action is great. So what does this mean? Let's say yeah, in the maze again, right? Okay, just look at the top right value. Let's say all the values are 1. Okay, so the agent will just maybe going up is great, and then it will go up, and then maybe when it's at state 0, it sees that the value of going towards the right is great. So you just explore. So this basically makes the agent like want to explore more, explore every steps. And then once the whole training process is complete, eventually the process makes the agent learn about, oh, this step is bad, instead of when it's when the table is filled with 0, the agent will learn, oh, this step is good. So it's kind of like opposites. So this optimistic initialization basically makes the agent more curious. But for our example, we will use zero initialization. Okay, so this is the Q learning training process. So let's say the agent is in state 3, here, taking action 3, going down towards the treasure chest. So you can see the Q learning formula. I just put it into words so it's easier to understand. Okay, so because let's use the formula. Okay, so because we initialize the entire table to 0, it will be 0 plus the learning rate. Let's set it to 0.01 times the reward, which is 1, because the agent touched the treasure chest. So it's a good thing. Then plus the discount factor, we set it to 0.9 times the max Q value in the new state. So the max Q value in the new state is 7, because the next state is 7. Okay. but it will be 0, not because you initialize the table 0, it's because it's the first state. Because like, so basically the next state, there's no good actions to take because there are no actions you can take. So it will be 0, and then minus the same thing at the start, 0. This will equals to 0.01. Then we just fill out the Q table. Yep. And then let's solve for the agent in state 2, taking action 2. So one state behind. So the agent is moving towards the right. And then we just plot the value. So 0 plus the learning rate plus the reward, which is 0, because we just make it such that there's no reward when getting closer to the treasure chest. Then we plus the discount factor times the max Q value in the new state. So the max Q value in the new state, you can see in state 3, the max Q value is 0.01. So we use 0.01 minus 0, and then equals to a very, very small number. So we put that into the Q table. So this is basically how the Q table will be filled out. So once you run an algorithm doing this, it will eventually fill out the Q table, and then the agent will know that what's the best action in each state to take. Okay, I'll just go through one more quick example. So I'll just go through the first one. So the agent is in state 2, taking action 1. So you want to go up and bump the wall. Okay, this one. Yeah. So 0 again, because the table is initialized with 0, plus the learning rate times the reward. So we want to penalize the agent from bumping into the wall. So let's penalize it with negative 0.5 reward. And then plus discount factor times the max Q value in the new state, which is 0.009. And then minus 0. This equals to minus 0.05. So you can see roughly from state 2, if the agent is in state 2, we can see that it wants to go towards the right instead of like bumping into the wall. So this is the worst option you can take, and this is the best action you can take. So the agent will move towards the right. So you can see that this is how agent solve an environment in Q learning. Okay, now let's move on to Q networks. Okay, so it's just the deep Q learning formula, which is slightly similar, just that the Q value, which we call it the quality, it will just be the reward if the new state is terminal. So basically, if the agent completes the game by reaching the end goal, it will just simply be the reward, in which case it will be 1 if it touches the treasure chest. If not, it will just be reward plus discount times max Q value in the new state. Okay, so first, the training process works by creating the main queue network. Okay, so first we create a main queue network. We initialize it with random weight and random bias. And then we make the target network, which is essentially a direct copy of the main queue network. So it has the exact same weight and biasness, but because it's all randomized at the start, it's like meaningless. So the first training process will be almost meaningless. Okay, it will be meaningless. Next step is step 3. The agent will navigate around the environment. So data is stored in this step, and I will go through, I'll talk more about that step in the later slides. Okay, so let's say the agent is in state 3 going to state 7. Okay, so because it's in state 3, we want to encode the entire state. So it'll be, you can see it'll be 3 zeros followed by 1. So this is called one port and encoded. And then we put this into the Q network. We will go through the Q. You will go through the network, and then we will get the output layer. So these Q values in the output layers, this pretty much mean nothing from the start. But yeah, so the main thing we need to look out for is, okay, I don't know what's negative here, but this will change later on. Okay, so each node at the end represents the actions. So because there are 4 actions that the agent can take, there are only 4 nodes. Next, we input the next state. So next state is 7. So here will just be 6 zeros followed by 1, and then 8 zeros. So we want to input the state 7 to the target network, and then we will get the. I skipped a few steps. But yeah, and then we will get the output layer. The Q values in the output layer is also determines the actions. So because the target network uses the DQ learning formula, let's use it here. Okay, because the next state is terminal, it's relatively easy. So it will just be 1 because the reward is 1. So we replace the value with 1 because the third node represents slowing down. Okay, next we compute the difference between the target and the prediction and update the main network. Okay, so what is the target and what is prediction? So the target value we want, which we use by using the deep Q learning formula, and then the prediction will just be the highest value. Okay, this is supposed to be 0.002. Let's assume it's 0.002. I made a mistake. So it will be highest value. So we will use this value. You will mean square error the two values to get 0.996. Basically, target value minus predicted value squared. Yeah, and then we update this value. So using back publication, and then we will, and this value will become 0.996. So after like a lot of training, the value here will eventually approach 1. So we know that this is the best action that the agent can take. Let's say if epsilon is a very low number and the agent chooses to take the best action. So, yeah. And then the next step is we repeat step 3 to step 8. So the agent just navigate around, go through the 2 networks, go back to the main network. Okay, so that's step 9. Moving on to step 10. After a certain number of episodes, which you can set, we sync the port. Okay, we sync the main network, not the policy network. We sync the main network with the target network. So we will copy over the weights and bias from the main network over to the target network. And then we repeat step 9 and 10 until training is done. So how do we determine if training is done? And set this up that after maybe like 1,000 episodes, the training will just automatically end. Or once the reward reaches a certain number, the training ends. So this is something we can set at the start. Okay, so let's talk about the experience replay. So the agent needs to store basically as much information as it can to solve the environment. Okay. If not, like you don't remember anything, you cannot solve anything. So what this does is it breaks correlation between the training data and prevents sequential dependency. But why do we need to do this? Because sequential experience are highly correlated. And then we need to use random sampling data to break the correlation. Okay. So what is a memory? A memory will be using a DAG. What a DAG is, it's a Python thing. So once you input a value at the start, once you put a value, it will be added to the DAG, and then the DAG will have a set size. So let's say 10. Once all 10 space are filled up, the oldest value will be thrown out. Okay. Okay, step 3. So we'll break step 3 into 2 parts, 3A and 3B. Yeah, okay. So 3A will just be we memorize the experience as the agent navigates the map. What will we memorize? We will memorize the state, what grid the agent is in, what action they take, what is the new state they move to, what's the reward they obtain, If not, it will just be 0. And whether it's terminated. Terminated basically means the game ends or the game never ends. So it will just be one of you. And then 3D, we play. So we will take a random sample from the deck and pass it on to step 4 for trading. So we will, let's say the deck has like 100. So we will just randomly take 30 samples and pass it on to trading for trading. Okay. So the deep machine learning formula basically is the Farama equation. Very similar to the Q learning equation. Basically is so the value or the Q value of state S taking action A will be equals to the reward obtained plus the discount factor times the max Q value of the new state as the estimated value function of the state. Yeah. So this equation is in deep Q learning. So now you know how deep Q network works. Let's move on to double DQS.
Okay, so now we're gonna go into double DQS. So obviously we learned that DQS are essentially using a neural network to compute a Q value, which is a value given to every action and state pair. But there is a problem with this. I forgot to add animations. So this might be a bit crap, but don't worry about that. So we have first the Bellman equation that was introduced in DQS just now. So this VS is essentially a function to give a certain value to a certain state. So recalling just now's space, for example, it will give a certain value function or a value to each grid cell in the maze. So we can split this up into different terms so that it's easier to understand. The RSA is essentially the reward function, which gives you the reward from taking a certain action A in state S. And then VS is just the value of the fixed state. So VS prime is what value you would get from going into the next state and following the best actions afterwards as well. So in total, VS is essentially the maximum expected total reward for the best possible action A in state S, which is immediate reward plus discounted value of the next state. And then we have a temporal differencing equation as well. So what the temporal differencing equation is essentially a function to compare like the error that we get. So it's comparing our prediction with the ground truth as well. So the TD error, we can again split this up to different parts. If we are looking at whatever is inside of the bracket, we have RT plus 1, which we call the immediate reward. And then we have plus gamma V ST plus 1. So VST plus 1 is the value given to the next state that you can get, or the next state that you'll be in, essentially. And then gamma is obviously the discount factor. And then we minus V of ST because we're essentially comparing what essentially our actual reward is from taking an action A state S compared to our initial prediction of being in this current state. So it quantifies the difference between the sample-based estimate and the current estimate. So meaning if TD error is a positive number, our current V of ST is an underestimate. So we obviously need to increase the value given to the value function with ST. And then if TD error is a negative number, that means our current VST is an overestimate. So we need to decrease that value essentially. So after basically understanding that part that's inside of the bracket, we essentially have this update function, which is equal to the temporal differencing equation. We just substitute whatever's inside the bracket with TD error. So it's VST new basically means the updated value of this state. And then we are updating the value as the old value that we gave to this state plus the learning rate times the TD error. So we are updating the value that we give this state with a small fraction of the TD error. So essentially like the difference that we have with our estimates. And then the problem with DQNs is that, again, recalling the Bellman equation, we are using argmax for the actions as well as the evaluation. And this is obviously not good because we are using argmax for both choosing an action to take as well as evaluating how good our action is. So this means that if the Q values, essentially the value that we give to a state is noisy, especially early on in trading, the argmax function will choose the action with obviously an overestimated value that we gave to it. And then the DQN will think that some actions are better than they actually are as well. And then this will end up causing the DQN to learn unstable or suboptimal policies as well. So yeah, we have an example here where like action A is actually 3.0. It should have a value of 3.0, but the estimated value is like 3.2. So these are overestimations. And then this is what double DQN does are basically. So again, the initial error is just we are using argmax for both choosing the best action as well as evaluating how good the action is. So we just have to split this up. We just don't use argmax for both choosing and evaluating an action, all right? So how we do this is we separate both of those, choosing and evaluation, to two different networks. And we have one online network and another target network. The online network is used for action selection, and then the target network is used for action evaluation. So now we separate both choosing and evaluating into two different networks. So this reduces the chance that we will essentially overestimate the value of a state. So just to note that double DQN actually doesn't eliminate overestimation bias. It just reduces it by making the value that we give to a state less optimistic, essentially. So this is how the two networks will train. We have the online network, which actively learns and updates itself via gradient descent, as you guys know. And then obviously we have the target network also. But the target network, there's two different methods for where you can update this target network. The first method is every, let's say, 1,000 steps, we copy all of the parameters from the online network to the target network. So this is called hard updating, because obviously we're copying every parameter, every weight from the online network to the target network. So it's just copying now. Right? And then there's a soft update also. So we have a variable tau, which is called the interpolation parameter. So it's normally closer to 0. Why is it closer to 0? Because a soft update essentially means that every step we will be updating the target network's weights with a fraction of the online network's weights. And this fraction is basically guided by this tau variable. So if I set tau to 0.1, essentially I am copying 10% of the online network's weights into the target network's weights. So when do you use DQN versus DDQN? DQN has a high overestimation bias, as we've talked about before, and DDQN has a relatively lower overestimation bias. So the complexity as well for DQN, like implementing it, is low, and the DDQN is also slightly higher because you're going to have to implement two networks essentially. The empirical gains for DQN is essentially you can use it for a baseline for small tasks, and then DDQN is just better for better stability in practice stuff. And then we move on to PPOs and DCNs as well. So Proximal Policy Optimization and Actor Critic Networks. So policy learning. The agent's goal, just to remind everyone, is essentially to interact with the environment and take actions that maximize the total cumulative reward. But obviously, the agent won't know like which actions are the best. It has to learn like which actions are the best. So it has to learn a strategy which tells you in what state has the best action, essentially. So for example, this card pole environment, if the pole leans left, you would want a strategy that tells you to go to the left, like move the card to the left so that you can balance the pole as much as possible. And then obviously if the pole moves to the right, you want your strategy to tell you to move to the right, like move the card to the right so that you can balance it. But how do you learn a strategy? There's two main ways. There's first a value-based method. So ignore the right side first. The value-based method is essentially what we talked about with DQNs. It learns a value function which gives every state action pair a value, a certain value, how good it is, how bad it is. And the state value function will tell you the expected cumulative reward from being in state S. So what is the reward of you being in state S and then continuing using your strategy that you have learned to take different actions from there on? Or you can also have an action value function, which gives you a certain value for taking a certain action in a certain state. So that's what the equation looks like. It's like argmax QSA, take the best action. And then obviously we went through this in Q-learning and DQN and reduce. And there's a new thing which is called policy-based methods. So what policy-based methods is different from value-based method, because value-based method, we talked about providing a value to a certain state or providing a value to a action state pair. But policy-based method doesn't assign a value, it assigns a probability. So it maps action probabilities without learning what values to assign to different state or action state pairs. So there's this equation. Okay, it looks damn scary, but it's fine. Like what it says is that this function is called the objective function. So the E over there is just expected cumulative reward, and then summation over every reward in the episode times the gamma, which is discounting factor, obviously. So the objective function just says the expected cumulative reward, essentially. And we want to maximize this, right? So we have to maximize it via gradient ascent, which is maximization of the function, essentially. And then the gradient for that objective function is shown in the below. So what this means is that the log likelihood of taking action A in state S, meaning it will be every action state pair will be assigned a probability map. And then the likelihood of taking a certain action A in state S and the reward given for taking an action A in state S will also affect the gradient that we get, which affects like how big of a change that we make also. And then the difference is obviously it produces probabilities for actions instead of a value. And then yeah, it's better for continuous action spaces obviously, because like with the value-based method, right? Like you're assigning a value to every state or assigning a value to every action state pair. But let's say you have like 8 million possible actions. How do you assign a value to every single action, especially when it goes up to infinite, right? So it's impossible. And that's why policy-based methods are better for continuous action spaces. And then now we have actor critic networks. So we went over policy-based and value-based networks. Now we have actor critic networks, where the architecture is using two networks, same as the DQN. But the difference is that this actor network is a policy-based method. And then the critic network is a value-based method. So how it works is that it relies on each other. The actor network will create actions to train the critic on, and then the critic network will obviously tell the actor network how good your action that you took is. And then the actor network obviously keeps on creating action for the critic network to train on, and then this cycle goes on and on. And then it will train essentially. So the actual cycle is that the agent observes a state S, the actor selects an action A in that state, and then the environment will give you your reward and your next state. And then your critic network will essentially compute your value estimate and PD error also from previous equation. And then the critic updates its parameters to train itself, obviously, to give better critics. And then the actor will update its parameters also using the critic's feedback. And then for these two networks, they can either be totally separate networks, so separate layers, separate weights, separate everything, or they can also share weights for the encoder or backbone. So essentially, if you have an image and you are doing feature extraction, you can share those weights. It's not a problem. Okay, now we move into PPOs, Proximal Policy Optimization. So what is Proximal Policy Optimization? It essentially aims to improve the agent's training stability to avoid policy updates that are too large. So you don't want to update your weights too much because it will be noisy. How it works is that PPO will clip the ratio of your difference between your current policy and old policy to a range between 1 minus epsilon and 1 plus epsilon. So in the paper, they use 0.2. So it's flipping the difference in the weights from 0.8 to 1.2. So this ensures, obviously, when you update your network, you don't want the update to be too large. You want to take smaller steps and be more stable in that sense. So yeah, great. And where you get higher or bigger amounts of gradient is when you have a high advantage value, which I'll go over later on. It should be fine. And then if your reward have very large variances, so if your rewards for certain action state pairs vary from like maybe you have a reward of 1 for taking a certain action in a certain state, or you have a reward of 50 plus 50 from taking a certain action in a certain state, then that's a high variance. So that's where you get like super large gradients and you have to clip it. So this is what PPO is basically about. So I mean, we can break down the equation into smaller steps. So the RT data is essentially the ratio of the difference from your old policy and your new policy. So it's essentially, you can think of it as, I mean, if you don't want to understand this equation, you can think of it as your new weights or your new parameters divided by your old parameters. So that gives you the ratio of the difference, right? And you're basically trying to split this ratio between 0.8 and 1.2 so that your weights don't change as much. You don't want like super big steps. And then your advantage function, obviously you can see here that your ratio difference is multiplied with an advantage function. So what an advantage function is essentially QSA is your expected rewards from taking an action A in state S, and then you continue following that policy to make further actions. So then is the expected cumulative rewards from basically doing that, taking a certain action in state S, and then just continuing using the policy or strategy. And then you subtract that with the expected return, basically your estimate of the cumulative reward you would get from just being in state S itself. So you don't have the cold hard truth of what the reward is that you get from taking an action A in state S. So you basically subtract these two, and then if your advantage is a positive number, it just means that your action was the action that you took was better than expected. So you want to increase that even more, essentially. And then if your advantage is a negative number, that means your action taken was worse than expected. And then you want to prevent that as much as possible. I mean, okay, if you don't understand still, where did my arrows go? If you don't understand still, this is essentially what it means. So imagine you are coming down from a mountain. You don't want to take very large steps. You want to take multiple small steps, and then you'll be more stable. That's the analogy, if you don't understand that whole part, because it was a lot of math. So yeah, that's what you can think of, I guess. Okay, then now the hands-on, which is okay.
You just want me to like give you the entire code, or do you want me to like type it out word by word? What do you guys want? Will me giving you the entire code like be more interesting than me like typing it out letter by letter? Raise your hand if you want me to give you the entire code. Can I just like walk it through? Okay, then what about the other option? You want me to type out letter by letter? Letter by letter, really?
You can explain more typing. explain the code or type thing.
Okay. Askia is like boring, but like type it out letter. Okay, we can do that. Okay.
We'll provide the PYM.
Yeah, actually, we should just give them like the bare bones, like I just give them all the marking blocks.
But how you going?
What you?
You can't do that now, but
Let's do it again.
we give the PYM after. Then you just type out word by word.
Okay, give me like a minute.
Like you just type out explain.
Is it so that like open collab?
You just type out explain. If you delete, it'll take a minute.
No, I already got that. Was very open. Wait, but like, I already have it, bro. You just have to. You can just send it to Discord. It take like 10 seconds.
We send it afterwards. Then you just type out word by word and explain the code at the same time. I think it's more understood.
Also, just like send it.
If you want to understand it. Yeah, I'm. We'll send the IPYMB like after the session so that you guys can refer back and then like add on stuff that I guess like you mistake or whatever lah. But for now you just type out and then like explain your.
Okay, so for this we'll be using a Google Colab. Yeah, just type in like Google Colab.
You increase it.
I don't think it changes, bro. Oh, you mean for me?
Yeah.
I need a charger.
Oh yeah, it changes.
I need a charger. Does a charger work for me?
It's okay.
Wait, give me a second. I need to charge on that. Is there any?
You understand? Yeah.
Can I click this?
Yeah, you can.
Hello. Can I still be heard? Okay.
Yeah, that's.
Okay, so we are going to solve LunarLander from Gymnasium. Okay, so if you don't know, Gymnasium is basically like this, like documentation where you can find a bunch of reinforcement learning environments that you can play with. Okay, there's like a lot of examples actually. So for example, for classic control, there's like all these environments. The couple which you saw earlier. I believe you also saw the mountain car and the pendulum, all of this. So these are like the basics if you want to practice. And then if you want to go like a bit deeper, yeah, you can train 2D games like robots moving and everything, car racing. Yeah, so for this we will be doing LunarLander because the other environments are boring. Okay, so just a quick run through of these environments. So the action space basically is the, does it say here? Yeah, okay, it does. So there are 4 actions you can take in this environment. First one is you do absolutely nothing, so you just fall to the ground to gravity, or you fire your left engine. And then second action is you fire your main engine, which is the engine below you, and then third action is you fire your right engine. So you can see here, there's like, if I zoom through, there's like one left, one right, and one bottom engine. That's the main engine. Okay, and then the observation space. Okay, it doesn't really say here for some reason. The observation space basically is an 8-dimensional observation space. So there's basically 8 dimensions. So the first 2 is X and Y. The X and Y coordinates of the LunarLander, so like exactly where it is in this environment. And then the third one is the horizontal velocity, followed by the vertical velocity, and then the angle of the lander in radians. So yeah, obviously like whether it's like upright or like slanted. And then the angular velocity, the left leg contact, the right leg contact. I think those are pretty self-explanatory. So okay, I think that's all I need to go through. Yeah, so this library is actually very useful if you want to practice your reinforcement learning. Oops. Okay, so let's move on to OLED. Okay, so there are two things you need to import. So the first one is you need to install. So first one you need to install the Swig. I have no idea. It's just like something you need to install before you install the next thing, which is Gymnasium Box 2D. Yeah, so you need to keep install these two things. Okay, if like I miss any code and then you just like haven't copy it down, just let me know. Okay, so while that's running, let's import all the stuff. Oh shit, there's a space here. Yeah, okay. So we need to import a lot of stuff actually. So we'll be using not TensorFlow. We will be using Torch. There are two core libraries used to solve reinforcement learning, or more like neural network stuff. First one is TensorFlow and PyTorch. So we'll be using PyTorch because it's more flexible. If you try out TensorFlow, you will know why. So we need to import Gymnasium, which is the library which I showed you just now. Import Gym. NumPy. Torch. Okay, so these are a bunch of like Torch libraries which we need to import. Random will be used for the epsilon later, the epsilon greedy algorithm. That will be used for the experience replay. And then we use matplotlib for plotting the graphs later. So you can see exactly what is going on. Okay, that's all. So this 9 imports. Okay, next, if your laptop has a GPU, we normally want to use a GPU because it's faster. If not, we will use your CPU. So how we do this is we get a device. Oh, sorry, this is CUDA. So what this does is, if you have an NVIDIA GPU, you will have CUDA. It will try to use CUDA if you have a NVIDIA GPU. If not, it will use your CPU. It'll be slower, but honestly, this is a simple environment, so it won't be that slow. So you can see your device with this, okay? And then if you try running it, this should be using, oh, I thought you have a GPU.
Oh,
Do you not have a GPU? Or maybe you don't have Fluent installed. Oh no, this is collab. Sorry, this is collab. You don't have GPUs on collab. So you automatically use CPU unless you, I believe you can connect to yeah, I think you connect to a GPU here if you really want to use a GPU. Okay, and then we need to set the random seed. So we need to set the random seed for reproducibility. So normally we use 42. Honestly, it's just like a sweet number that we use everywhere if you do like machine learning and deep learning. So 42 for everything. Okay. Okay, next. Yeah, so we are using GPU right now because I set to a GPU runtime. Okay, next let's make the deep Q network. Okay, honestly, this whole code isn't really that long. So let's set the class for DQN. Okay, and then we need to initialize it. So we will input 4 things. The input state, the number of nodes. Okay, if you don't know, I cannot like multitask, so I will sometimes like type out what I'm saying. Okay, so these 4 things. Okay, next. Okay, so here we define the network layers. Okay, so we will have two fully connected layers, followed by an output layer. So if you guys remember, the first fully connected layer will just be your states, and then the output layer will just be your actions. So your input states, the nodes. These nodes you can set later. Normally we use like 1 to 8. Normally you'll be in we call power of 2s. Yeah. So it'll be 2, 4, 8, 16, 32, 64, 1 to 8, and so on. But for this you'll be using 1 to 8, which we will initialize later. Okay, so we need to use the same nodes here. So how does this work? So the input stage will be just the environment data, and then the nodes. So these nodes, 2 nodes needs to be the same. If not, the data can't pass through. And then we use the H2 nodes for the output layer. Okay, so this is our deep tune network. Now we need to make a forward function for this class. Okay, so for this forward network, this forward function, we will be using value activation. So what is value activation? Basically, okay, so normally for neural networks, you'll be using a lot of this is really you'll be using a lot of activation functions. Okay, value activation. So what this does is, if the number is negative, it will be 0. If it's positive, it will just be its number. So for example, if you get like -10, it'll become 0. If it's 10, it'll be 10. That's all. This will be FC2 fully connected. FC basically just means fully connected layer. Okay, so this is our entire class for DQ network. Okay, we will be using 2 of these later. Okay, so let's move forward to the experience replay memory. So if you guys remember, the experience replay is a very important component of DQN, and it helps to break down the correlation between consecutive learning. Okay, so we'll be storing a bunch of stuff. We're storing the state action. Okay, I'll just write it down. Experience replay, store the state action, the next state, and done. Okay, done will just be like terminated. Wait, I'm missing something. The reward. So state action reward. Yep. Okay, so we initialize it with a class again. We call it a replay memory. So we initialize it with a parameter called max length. So we want to limit how big the deck will be. Okay, because we don't want to store all the memory, and all the memories will be thrown out. Okay. And then we need to add a function to append into the deck. The next is the sample. So sample will just be, we will randomly sample a set amount of data from the memory. So you can set sample size later on in the training function. Okay, lastly, we will get the length of the deck. Okay, these are pretty straightforward. Okay, so once we got the deep Q network and the replay memory, we can start making the training function. Okay, you see, honestly, it's not that much. There's only like 3 cells you really need to type out. Okay, but this cell is pretty long. Okay, so first let's define the training function. Let's call it the train DQN. And we want to train it for, let's say 1000. Okay, so before we train everything, we need to initialize a few stuff. Okay, we need to initialize all the parameters. So first one is of course the learning rate. Set it to oops. And then we have the discount factor, which is gamma, to a high value because we want long-term rewards. And then we have a memory size. We set it to 50,000. Okay. So memory size is basically the replay memory. And then the batch size. So the number, this also related to the replay memory. This is the number of experience you sampled per training step. And update frequency, we set it to 4. So update frequency is basically the number of steps between the network updates. Okay, next, the target update. So this is the steps to number of steps, number of episodes between updating the target network. We set it to 10. And then the epsilon. Let's set it to 1 for now. And then the epsilon n. So epsilon n is the lowest value of epsilon you can get. So we want to set it to 0.01. And then there's the epsilon decay. So this will just be the rate at which the epsilon will decay at. So basically the rate at which exploration will decrease. We set it to 995, 0.995. Okay, and then there's the hidden layer. Okay, this will be used for the deep Q network later. Oops, 1. Okay, these are all the variables, the hyperparameters that you need to set. So this is just the default one. Honestly, it might not be the best. This is why you need to train your hyperparameters, which is like a very big thing if you are trying to achieve the best score possible. Okay, next we initialize the environment. Okay. And from the environment, we can extract a bunch of stuff. So the first thing is we want to extract the dimension of the states. Okay, this will be it because as seen in the document just now, it's an 8-dimension shape. And then the actions. Okay, this will be 4 because there are only 4 actions you can take. Okay, next we want to initialize the neural network for the DQN. Okay, so remember just now we made the class DQN. Okay, so first I'll just call it policy network. Okay. So remember just now in the slide we called it the main network. Policy network and main network are used like interchangeably. So let's call it policy network for now. So input the end observation, the hidden size 2, and actions to your device. Okay, this is the policy network. Next, we will need to make the target network. Okay. I will just let me tell these options. Okay, honestly, it's just the same thing. So just copy and paste. Because both of them are identical at the start. So right now, oops. If you remember the deep Q learning training process which I ran through earlier. Yeah, so we are creating the main Q network, and then now we are making the target network. Okay. Okay, so next we need to copy the weights and bias from the policy network into the target network. So both of them both of them are exactly identical. Target. Okay, and then we need to set a target mode, set a target to evaluation mode. So you can do this by calling it just doing eval. Yeah. Okay, next we need an optimizer. So what is an optimizer? We'll be using Adam optimizer because it helps to adapt the learning rate for each parameter. So basically in every neural network, you basically need an optimizer for the network for it to update the network's parameter during training. Okay. So for this we will be using Adam equals to And then we set the learning rate to the learning rate which we set just now. Yep. Okay, next. We need to initialize the memory. Okay, not the last one. Not the last thing we need to initialize, but we're getting there. Okay, so the memory will be the experience replay buffer. Okay, so the replay memory set to the memory size. Okay. I don't know why there are like no colors here, but okay, next. We need to initialize the rewards, losses, epsilon, steps, total. So all these are used to store the training metrics for analysis and visualization. So this will all be used for graphs, which we will show later on. So like if you don't want to see any graph, you don't need to do this. Okay, so reward basically stores the reward for each episode. Losses, the loss, the lower the better, epsilon, and the number of steps. Okay, pretty standard stuff. Next, we initialize the epsilon. Okay, last thing. To the epsilon start. So it'll be 0. I mean, it'll be 1. Okay, now we can finally make the training loop. Okay, here's the more interesting part. So for episodes in range, so this will be 1,000 lah, because we set episodes to 1,000 to 1,000. Okay, then we need to reset the environment to the initial state at the start of each episode. So, okay, never mind. I can't show you guys the video, but you guys will see why. You guys will see this in action later on in the video. Okay, so we reset the environment. Next, we need to convert the state to PyTorch tensor. So we can't just like input a normal list or a normal tuple. We need to use torch. We use tensor. So the state data type will be the torch. Will be float. Will be a float. Yep. Okay, and then we unsqueeze it. Okay, so if you don't know what unsqueeze is, it basically converts like, let's say we have a list of 1, 2, and then we just make it to, let's say 1, 2. It'll become 1, 2. Okay, so this is basically what unsqueeze does. Okay, next we need to initialize a few simple variables. So done equals to false. So this is to indicate whether the episode termination is due to success or failure. Okay, next, truncated. Okay, truncated basically means whether the episode ended because it reached the time limit. So the environment has a time limit. If you like keep on flying for like, I don't know, an hour, something is wrong. So the environment will automatically reset. Total reward set it to 0. And we have the episode losses. Is to record the losses for the episode. Okay. Now the actual training process. Okay. So while the training process is not done or not truncated, and then we need to use the epsilon greedy selection. Okay. So if you remember, the epsilon greedy will basically determine whether the agent will choose a random action or the best action from the policy network. So if random dot random less than epsilon, you will choose a random value. Oops. So this will allow the agent to learn new strategies to explore the map more. Else, okay, so what this does is basically it chooses the action with the highest Q value in the Q network, the policy network. Okay. And next, we need to execute the selected action in the environment. So we will have next date, reward, done, truncated, and the terminator or no. So we leave it as blank. Equals to env dot step. So this basically allows the agent just to like take the step in the environment. Okay. Then with the reward, we add it to the total reward. Okay. Okay, and then we need to convert all the observation data to PyTorch tensors for both storaging and processing, because yeah, you cannot just like input the reward or anything into a neural network as itself. So reward equals to torch dot tensor. Oops. Okay. And then the next state, same thing. Data type will just be float again. Okay, sorry, there's no. Yeah, okay, and then we unsqueeze it. Okay, last thing, the done tensor. Okay, so you can see like there's a pattern for all of them to convert them to a tensor. Okay, next. So we are right here now. So we need to store, remember there's 3A3B, we need to store all the data into the replay buffer. Okay, so moving back to collab. Okay, oops. Oh, okay, I was so confused. Okay, so we append the state, the next state. Sorry, the state, the action, the next state, the reward, and the terminator or not. Okay, so now that we input this into the replay buffer, we can update the current state for the next iteration. So state equals to next state, every steps. Total plus equals to 1. Okay, so here's the part where the Q network will be trained. Okay, so if the memory, so we only want to train when we have enough experiences and at the specified frequency. Okay, so that's why we need this if statement. If the memory above the batch size, because we need to extract out a batch size from the memory, right? If there isn't like a enough memory, then like there'll be a bunch of errors. Okay. Next, we want to sample the random batch of transitions from the replay memory. So we sample the memory. Dot sample. Oh my god. Okay. So next, we need to transpose the batch for easier access. So we will convert the list of tuples to a couple of lists. So at first it was like, let me give you an example. Like, let's say S1, A1, and so on, right? And then I'll make a S2, S2, A2. So at first it was like this, and then we will convert it to yeah, you get it. Basically, we just swap the list and the tuples. Okay. So and then now we need to extract and combine the batch components into tensors. Yeah, these tensor stuff are like damn annoying, but we need to do them. So state batch equals to prox.get action. Okay, this is what I'm going to do. next state batch, reward batch, and done batch. And then we just change the numbers. Because these are all in orders for each tuple, for each list in the tuple. Okay, next, we need to calculate the Q values for the actions that were taken. Okay, so state action values. So this we will be putting the state into the policy network. So right now we're doing this. So input state, this part, step 4. Yeah, so this returns a tensor of shapes with Q values for each action. So this will essentially be this. Okay. Okay, next, we need to calculate the target Q networks based on the Bellman equations. Okay, so next state values. So we first initialize it with 0. Okay, then we need to only consider future rewards for non-terminal states. Okay, with thoughts. Training the target networks. Oops. Okay. Just like just want to check if everything's correct. Okay, next we need to compute the target Q values using the Bellman equation, which I went through earlier. So it's reward plus gamma time next state value. So expected state action values. So we are going through this part now. Wait, no, not this part now. The discount factor times the next state value. Okay, next we need to calculate the loss. For this, okay, because I tried it with mean square error loss. Wait, where is it? This part, okay, so this is the mean square error. I tried using mean square error, but because this environment is a bit more complicated than a simple environment, the training process didn't really work out well. So for this, we will be using Huber loss. So because it's more robust to outliers compared to mean square error. So what this loss do is basically measures how far the current Q value estimates are from the target Q values and provide the direction to update the Q networks. Okay, next. Okay, actually we are coming to the end soon. Next, we calculate the loss. And then we add it to the episode loss. Episode losses. And okay. Okay, next we need to use the standard neural network optimization step. So this is for training the network. And then we backward propagate the loss to train the policy network. Yep. Okay, and then for this we'll be using gradient clipping. This is something extra. To prevent the gradients to prevent exploding gradients so that it doesn't like overfill or anything. Okay, so there are actually two things here which I added in to make this DQN better, because when I use the normal DQN, okay, let's say the agent didn't really learn. So I'd use something extra. And then we update the network parameters. Okay. Okay, next we can break out this loop. Wait, okay, it's so difficult to see without the lines indicating which tab I'm on. Okay, so this thing actually has to be one more tab. So I of this and Yeah, this is supposed to be in the while loop. Only this is the epsilon greedy algorithm. Okay, next we just update the target network. Every certain number of steps which you can set. So we assign it to target update. So if episodes if it can be divided by target update, we will update the target network. So this updates the target network. So this will be doing here. So we are at step 10 now. Okay, step 11, the last step. We need to decay the epsilon. If not, the epsilon will like never decay at all. And then we will forever be exploring the map and never taking the best action. I have epsilon decay. Okay, and then we just record the metrics. So rewards, append the rewards, total rewards. And epsilon 2. Yeah, and then we only append if we have the training steps this episode. So if episodes losses okay. So I have no idea why this mind like doing this. Okay, and then because we want like verbosity, we want to track the printing process. We can use this. If episodes, for every 10 episodes, we calculate the average rewards. Oh my god. Okay, then the next few equations are damn long, so I am just going to copy the entire DQ network. Are you guys in the Discord? Because this printing process honestly is just a pain to type it out. Okay, I'll send it in. RL training. Okay, I'll send the entire training step. So sorry if you guys like actually type everything out. So this is with the comments. This is how you type out.
Yeah.
No space already. Oh, okay, never mind. It's too big, so it will just remain as a text file. Okay, so if you just copy everything and you replace it, okay, basically this. course, you guys can see why. Okay. Oh shit. Yeah. Okay. Oops. Yeah. Okay. So this was the thing that I was damn lazy to type out. Okay, and because of time constraint also. So yeah, after that, after we print out the printing process, so we want to print out the episode, the last 10 average, the last 100. So these are just like the so-called moving averages, epsilon and loss. Okay, and then we save the model to this path. Okay. Next, we want to plot the result. So we use matplotlib. Yeah, 131 means 1 row, 3 columns. And then we plot out the rewards, the epsilon. We plot out the rewards, loss, and epsilon. Yeah. And then we save it. We save the image now, basically. Okay. So now let's run off. And you guys can see the entire training process. Okay, if you guys if you guys missed anything on your code, don't work, right? I'll send the notebook over. Okay. Okay, so while he is running, I'm gonna go to the toilet real quick. Make sure you're running. If not, just like upload the entire thing. Did it run? Okay. Oh shit. Where's the mic? Sorry, sorry, I'm getting for the function. Yeah, okay, so we need to just train a model by calling the function. Then we can evaluate the agent. This evaluate agent is done. Sorry, I haven't initialized the code yet. So yeah, we need to initialize the agent. Okay, for time constraint, right? Because we're supposed to end at 4:30. Can you guys just like copy the notebook in? If you guys have access to this channel, RL training, just download, and then just input it inside. Yeah, so there are like comments, a lot of comments for you to read if you guys don't understand what each step does. Yeah, so this is the evaluate agent function. If you're using if you're doing it locally, right? There'll be a pop-up from Pygame. There'll be a window pop-up where you can actually see the agent playing the environment in real time. If not, it'll just not show in the window. Yeah. So if you guys are running it, why is it taking so long? Okay, yeah. Right now it's importing all the stuff. But yeah, it's a very weird like icon for some reason, so just be careful. And then it should run here. Yep, so right now it's training and logging the episodes every 10 episodes. And then you can see that the last 10 average, the last 100 average will slowly go up. Epsilon will also gradually decrease, and the loss will also be decreasing if the agent is learning. Okay, so we set it to a maximum of 1,000 episodes, but the training will automatically stop once we deemed it as fully trained. Means we set it to stop after you achieve reward of 200. Read the offline on what that they just kind of more gymnasium and things like
Oh, it's the- it's about- oh,
just like
training,
uh,
not a training, like, training.
more this student. Okay, this is a library style like doing
Oh,
with the book.
yeah, like, it's just the, then the model you want to use. I mean, model it's
Yeah, yeah, I just placed it. Okay, so while we're waiting for it to train, I've input this link into the Discord. So this is table baseline tree. It's basically a library containing a bunch of LL algorithms where you can customize to train your, let's say, custom environment or your gymnasium environment. So you can see in this code, right, the carpool V1. So carpool will be classic control carpool. Yeah. So for this environment, you can just solve it in like 11 lines. Yeah, instead of like coding the entire network, the entire logic. Plus, this is using A to C, which is way longer than DQN. Yeah, so you're using a GPU, it should be way faster than mine. Nope, nothing else. We're just waiting for it to train. I think like for this is yeah, it's not that
when you're using CPU.
it's okay, it's really like 1.5 minutes. If you won't reach 1000, maybe reach like 800. So actually like maybe like in 20 more seconds. I said stop condition. I said a stop condition. I make it train all the way. I make it stop, right? Maybe then that's right. Yep. Okay, yeah, so you can see that training is done, and you can see that the environment has been solved. Yeah, if you run this if you run this locally, you will see a pop-up where you can see the agents of the environment in real time. You will see you can see there's a video. Shit, that's in a wall. I think I feel something in this 90%. Shit. So it's like a P. Just the P. Actually, even I don't think I can see. Then you just like you just see it in the action. Yeah, so it's shit. Okay, so you can with all of these saved models, you can actually extract out the video. If you cannot run it locally, there's a way to record the run through. It's called gym.rappers.record video. If you take a look at it, you have to look. Okay. Other than that, yeah, the agent has learned, and Yeah, if you actually record a video, I assure you that the agent has learned and it has landed in between the flags. Yeah, so you will like land in between these two yellow flags. Yeah, if you guys have like any questions about the training process or anything, you can just like come up to the client and ask, or like you can message in the Discord. Yeah. Thank you. Go ahead. Let me do.
Yeah, that's basically like, do you guys have any questions or whatever? If nothing, dish it out or
Is it?
you said this
Yeah, it does.
always contribute on this.
Oh, okay. Okay, wait. Let's try this. Let's just do how many episodes. Oh, fuck. Every episode. Shit. Oh shit. Sorry.
Absolutely.
Okay, set it to like. Shit. Oh. Every 100. Wait, let me use the mic. Okay, so if you want to like see the training process throughout the uh training process, yeah, you can just add this code into here. Okay, so I set it in the Discord. It's here. You just copy this and you replace it here. This one. And then it will save a video every 50 episodes. You can change it like you can change it to like set. You can change it to save a video every single episode you want to. Just change this. Yeah. If not, yeah, that's like you can just go now. Or you can wait and you can see the video. Yeah. Okay, so episode 0. Oh, okay. No, okay, so because episode 0 is landed into the thing, into the target. Let's see episode 100. Oh, okay, this is because I really trained you. Wait, let me stop. Oh yeah. And I can see in episode 100, the agent failed. But you land outside the area it's supposed to land in. Yeah, then you can just see that eventually over time the agent starts to learn. Yeah. Yeah, okay, that's all.
Oh, yeah. But if you guys have any questions, just ask us.
Okay. Super, this is kind of the next one. What are you doing? You laugh like that.
Reminds me of an SPA lecture.
He then falls asleep, so they would person they can person if Sure.